Hello everyone and welcome. This video is all about eventual consistency models. We will explore different consistency guarantees in distributed systems. So let's dive in and get started. First, let's understand what consistency means in distributed systems. We'll compare two main approaches: strong consistency and eventual consistency. Strong consistency means that all reads will reflect the most recent write. In other words, all replicas return the same value, and there's a linearizability guarantee. However, this often comes with a high latency cost. On the other hand, eventual consistency allows temporary inconsistencies. Given enough time, all replicas will converge to the same state. This provides lower latency and higher availability, making it suitable for many real-world applications. Now let's explore some types of eventual consistency models. First is causal consistency. If operation A happened before operation B, all processes will see A before B. Concurrent operations, however, may be seen in different orders. Next is sequential consistency. All operations appear to have executed in some sequential order, and operations from each process appear in this sequence in program order. Let's explore more kinds of eventual consistency. First is monotonic read consistency. If a process reads a value of data item X, any subsequent read operation on X by that process will always return the same or a more recent value. Next is monotonic write consistency. A write operation by a process on a data item X is completed before any successive write operation on X by the same process. Now let's delve into more eventual consistency models. First is read-your-writes consistency. The effect of a write operation by a process on data item X will always be seen by a successive read operation on X by the same process. Next is writes follow reads consistency. A write operation by a process on a data item X following a previous read operation on X by the same process is guaranteed to take place on the same or a more recent value of X that was read. Next, let's talk about how to implement eventual consistency. A crucial aspect is conflict resolution. Common strategies include last write wins, where the write with the latest timestamp is chosen; vector clocks, which help to track the history of writes; conflict-free replicated data types or CRDTs, designed to avoid conflicts; application-specific merge functions to resolve conflicts based on business logic. CRDTs are particularly interesting. These include state-based CRDTs, or CVRDTs, and operation-based CRDTs, or CMRDTs. Examples include G-counters, PN-counters, and OR sets. Let's explore some real-world applications of eventual consistency. First are NoSQL databases like Cassandra, DynamoDB, and MongoDB use eventual consistency to achieve high availability and partition tolerance in distributed environments. Next are content delivery networks, or CDNs, like Cloudflare and Akamai use eventual consistency to propagate content updates across globally distributed edge servers. And also collaborative applications, Google Docs, Figma, and other collaborative tools use eventual consistency to allow multiple users to work simultaneously while resolving conflicts. Here are the key takeaways from our discussion on eventual consistency models. Some of the benefits of using eventual consistency models include higher availability during network partitions, lower latency for read and write operations, better scalability across distributed systems, and improved performance for geographically distributed users. When considering eventual consistency, you should choose the consistency model based on the application needs, implement proper conflict resolution strategies, consider data visibility requirements, and balance consistency versus availability trade-offs. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.